Hello, hi to all. This is Guillermo from STT in Spain. I would like to say hi to all friends and all the people that is coming to this webinar event that we are doing today. I am the key account manager inside STT in the area of Motio. STT is a company based in Spain with a lot of experience. We have 25 years of experience in motion capture solutions, mainly analysis solutions. We are a software developer company. And today we are here to explain with the help of Borut Fonda from Slovenia, the cycling kinematics and bike fitting fundamentals. Borut Fonda is a professional bike fitter. He is a PhD in sports science and very skilled in cycling kinematics and bike fitting analysis. I would like to say hi to him, and he will join this webinar, and he could start with the presentation. I would like to say also to everyone that after this presentation, that will take probably 35 minutes, we will have some time for questions, okay? So questions will be done at the end of this webinar. So without wasting too much time, please, Borut.
Hello, Guillermo.
Hi, how are you?
Hi, thank you very much for inviting me again for a webinar, and hello to everyone who's joined. And happy to be here again and to present some fundamentals, the basics of bike fitting, and share some knowledge we've collected over the last several decades. Yeah.
Okay, great. Then I will leave you with all the audience, and I will be on the backstage. So everything you need, just let me know.
Okay.
Thank you.
Guillermo.
Thank you to all, and welcome to this cycling kinematics and bike fitting fundamentals.
Okay, so I think you see my screen now. So that's all good. So thanks again, Guillermo. Thank you, STT, for the trust, for the support, for everything that we've been doing together for the past few years. So today's lecture, we wanted to do a step back in terms of the depthness of the knowledge and everything that we're sharing, and literally speak about the fundamentals. So when we speak about the fundamentals, we often want to go, what are the first steps? So this presentation, this webinar is mainly targeting the beginners in bike fitting, how to start, and not those who've been doing bike fit for several years and been working maybe with more complicated cases like injuries or really high-end performance cases. But nonetheless, all of you are welcome to question everything they do, to criticize, to ask questions at the end. So a little bit about me. I have a PhD in biomechanics and motor control from the University of Birmingham in the United Kingdom, and I worked quite a lot in cycling sphere, especially from the biomechanics point of view and motor control. I'm also a former international cross-country rider, so cycling's kind of in my blood since the beginning. As you can see on the pictures, I started quite early. Also a lead scientist at Absolute Black, helping developing new products that can help cycling better, faster, and more efficient. And former and still external assistant professor at the University of Primorska. But most importantly, probably for this topic, apart from the scientific background, is that I work a lot with professional cyclists. One of them is currently wearing pink jersey at the Giro d'Italia, probably one of my best references. We've been working with today for the last, well, since he turned pro. So this is going quite well, and we can have a discussion about this as well. We had some webinars before with STT, and I think both of them are also freely available on YouTube. Now, when if I would know that all of you have watched this YouTube, this presentation would probably be a little bit shorter. So, but because I don't know how many of you have actually watched the previous baseline webinar, which speaks more about the technical background of the kinematics, I'll have to repeat certain aspects, and that's mainly in terms of methodology, how kinematics work, and what makes them reliable, and what's the difference between different motion capturing systems. At the same time, what I would like is to invite you on a masterclass that we're organizing as part of the Science and Cycling Conference in Florence. Unfortunately, I was told yesterday that it's almost full. So if this is something that's interesting, I think there are 1 or 2 spots still left open. So Science and Cycling is a great scientific conference, mainly focusing on cycling. So from physiology to nutrition, technical aspects to biomechanics. And every year there are several master classes, and this year myself and Team STT were organizing Kinematics Masterclass. This is, in my opinion, the best way to really get the in-depth knowledge of how kinematics works, because we're going to speak about the technical setup, all the problems you'll be facing, and you will actually get the hands-on experiences of how to actually do the bike fit. So we'll have a full setup there. We can try different scenarios. We'll actually be doing bike fits one-on-one on one full day. So if this is something that interests you, visit the sciencecycling.org and try to get your spot. And maybe even if it's full, try to be in a waiting line if someone cancels the last minute and you get your opportunity. So on to today's webinar. I'll try to keep it short and concise and maybe leave more time for the questions, but we'll start with a bit of an introduction and then kinematics overview. This is what's going to be repeating the previous lectures, and then we'll go to the bike fit fundamentals. Now, most of you, at least those of you who have been who have knowledge in bike fitting, you know it's not a very simple, straightforward process to follow one collective variable and say that's it, that's how you need to do it, like saddle angle, knee angle, and that's it. And unfortunately, it doesn't work like that. But you have to start somewhere. So what I tried to do with this lecture is to focus on the 4 or 5 different points of view and have them as a baseline. Whenever you're going to have a client who has a problem, an injury, discomfort, or a special performance requirement, most of the times those fundamentals may not work as clearly as they would with someone who's got basically no problems on the bike. So, and at the end I'll show you one example which I really like to use when kind of summarizes the whole lecture. So a bit of an introduction of bike fitting, how everything started. There's quite a few scientific papers, but still, in my opinion, there's a big lack of scientific papers, really high quality scientific papers that could explain bike fitting into more detail. Bike fitting, it's even the terminology itself is very commercial. It's not so scientific. So we prefer to use the terminology biomechanics of cycling, and how certain interaction as body position work in that respect. But if we look some of those papers, I would strongly advise you to look at the later 2 papers. So one is actually my paper that we published back in 2014. In Journal of Sport and Sciences, speaking about how different kinematic methods actually differ between each other. So it's a very important paper when you're going to read all the other papers and you're going to say, right, this author said that you need 25-degree knee angle for optimal performance, but without knowing how they actually measure that knee angle, that information is totally pointless. And the last one, which I would say was kind of the revolution of the papers as well, of the scientific papers as well, is from a good friend of mine, Jeroen Swart and Wendy Holliday, South African scientists. It's a review paper on cycling biomechanics optimization and how the bike fitting evolution or revolution happened in the last few years. proposing some of the new methods. So these two papers is something that I would suggest that you guys dig into and then start exploring into more. But how everything started in bike fitting, it's quite funny. We have to go quite back into 1972 when the Italian Olympic Committee issued or published this handbook, which is basically a handbook of cycling. From the mechanics, training, nutrition was one of the first handbooks written on the cycling area. And on one of their pages, they also speak about the position, how you should be positioned on the bike. And if you actually look way into the text, you will see that the first recommendations happened that they invited a group of 20-year-old professional cyclists and assuming because they rode fast that this is how you have to sit. And that's it. That's how bike fitting started. That was the first recommendation ever done, ever published. And basically everything, even now, you will see people referencing back them, how the bike should be positioned is based on this very low quality approach of studying human biomechanics. So this continued, and we are now in an area of IT exploding, having a lot of the possibilities. The technology is allowing us a lot more. And if we look now, basically recording 3D kinematics in real time, especially STT, in my opinion, by far the best system you could use in daily practice for capturing motion capturing system for cycling biomechanics. It's accurate within 1 millimeter in a 3D-dimensional space at the very high frequency, which is like 100 hertz. And everything's super simple and smooth. The workflow, riders like it, they're in the center of attention, and we got quite far. So if we're looking from 1972 until now 2024, the actual progress made was very big. This, I would say, is currently also most state-of-the-art system that can be used for bike fitting in terms of kinematics, to be clear. There are other aspects of dynamics, pressure mapping, and so on that I will intentionally not cover in this webinar, but I'll focus on the kinematics only. So a little bit about, as a brief overview of the kinematics. You want from your system, regardless what you're using, is that a manual goniometer, which is kinematic? Is it your iPhone or an application within your iPhone? Is it a tablet high-speed camera or a very expensive motion capturing system like Vicon for several €100,000? There are three criteria that needs to be met. One is accuracy, repeatability, and sensitivity. Once all these criteria are met, that the system is accurate, that it actually measures what it measures, that it's repeatable, that when it's measuring the same thing, it always measures with the same result, and that it's sensitive enough for the change when you make, for example, a 3 millimeter increase in saddle height, that it actually detects some differences. And once that's met, we call this that the system is valid. It can be used, this is validity, it can be used for bike fitting. And I can tell you first-handed that I've tested a lot of systems, and STT with their system, motion capturing 3D-dimensional kinematics, is a valid system to use on a daily basis for kinematics. There, of course, is a certain error of measurements. We cannot say there is no error of measurements, but it's got nothing to do with the system per se, but it's got to do with the experimental setup. And just for example, when you place the markers which the motion capturing system will detect and record, these markers are, in some cases, are attached to the skin. In some cases, they're attached to the lycra. And lycra moves, skin will be moving because it just travels through the bone. It needs to be flexible. So what you have to do is basically to follow certain guidelines that the manufacturer provides and place the reference positions when you're placing the markers. So if your interest is in, I'm really interested, for example, in knee angle at the maximal extension of the leg, then place the markers on the bony landmarks when the leg is fully extended. When you place the markers, for example, if you're interested in where the knee is or how the knee travels up and down at 90 degrees, then make sure you're going to place the marker on the greater trochanter and the lateral condyle, lateral malleole, for example, when you acquire the position that you're interested in. So this is a certain aspect that cannot be ignored. Then, for example, when you have lycra, if it's all fluffy, make sure you can attach it, or maybe ask the client to remove the jersey if that's the possible. Just basically do anything to remove this error of measurement that is per se present in acquiring human motion. So what can be done to reduce the error of measurements? Of course, you can acquire a certain number of cycles. For example, nowadays, this is totally possible. Back in the day when scientific literature started, there was a big problem. It was the problem of the computer memory. And for example, one of the studies that looked at biomechanics of cycling, especially pedal forces, their force system was very, very advanced. Even nowadays, it could be compared to what we use in 2024. But the only problem they had was they could only store a certain amount of data. And that data normally was for one pedal revolution. And then they had to take the floppy disk and analyze the data by hand and record another pedal stroke and another pedal stroke. And basically they would use one full day just to analyze certain positions. So you can imagine the research was quite harder. Nowadays, with, I'm not going to say unlimited memory, but enough memory to record 30 seconds, 40 seconds, 1 minute, you record certain movement. In this case, this is knee angle, knee flexion that's changing through the cycle for one leg. And when you cut the cycles, you form something that we call an ensemble average. An ensemble average is basically plotted all the signals one-on-one and take the average value of all that. Now, the information like that already tells you a lot because it speaks about the variability. I don't want to speak about the variability too much now because that may be a little bit more in depth. We'll definitely speak about this on the masterclass in Florence, but variability is very important. So someone who's less variable, their movement is much smoother and it's always the same. Whenever you're going to see a lot more dispersion of the data, the variability is going to be higher and you're going to see this graph here much bigger. So the plots will not collide as well as in this case that I'm showing right here. Yeah, so going back to in STT 3DMA software, that's done automatically. And that saves you a lot of time because when we use this in scientific literature, we record and then we use some pre-programmed scripts, and every time we need to program and process the signals. But if you have this in real time, literally at the click of stop within few seconds, that's what you get. So the result that you're reading in the data in the tablet, and you want to make some conclusions, basically what the knee angle is, what the knee trajectory is. In that case, you want to have a repeatable and correct, valid information. Only in that way this is possible. So you may already be wondering, hey, what about the physiotherapists who are using the manual goniometers? Well, in my opinion, in cycling, that doesn't really work well in terms of reliability, even though some studies showed, on contrary to what I'm saying right now, but all the experiences I had when you're doing 1 measurements, 2 measurements, even in that case, you would have to read at least 3 to 4 times at the same position to get the valid information. So what are we looking as a bike fitting based 3D kinematics? There are certain body angles, and today we're going to focus mainly on the lower leg, then the trunk angle, and some other examples as well. So basically, when you have marker set covering the full body, you can analyze almost any angle you want. Again, STT software allows you basically to measure all the angles in every single plane from movement and center of gravity, about which I'll speak a little bit more in the later phases of this webinar. So going on to the actual practical side of the talk today, we're going to speak about those fundamentals. And when it comes to bike fitting, what's most important is basically the interaction between the contact points. And our contact points, we have the 2 contact points on the handlebar, 2 on the pedal, so left and right pedal, and 1 on the saddle. And everything here in between, in terms of biomechanics in the lab, it doesn't really matter. Is it an aero frame or is it lightweight frame? Is it steel, a carbon fiber, or from bamboo? It doesn't matter. They are the contact points, those that matters, and this need to be set in the right synergy to make the body flow work well. So what we're going to look when you, for example, change this contact point, you can change the saddle type as well. But again, I'm going to be intentionally skipping the saddle types and saddle pressure. You can change the saddle height. By that, you will change the angle of the lower extremity. You can change the fore and aft position, and you can play with the center of gravity, and you also, again, affecting the kinematics of the lower leg. And you can obviously change the angle of the saddle, and that's going to directly influence the lumbar inclination of the spine. Then we have the clit position. Now, clits itself allow us to kind of dictate where the knee is going to travel. So the orientation of the clit, especially, not so much the fore and aft position, but the orientation is going to dictate where the knee is going to travel. So again, by adjusting the clits, this should be one of the foundations of or fundamentals of the bike fitting. And then we have the handlebar. Now, in the last decade, cycling industry complicated our lives, or in some ways even simplified it, because there's not much to change. But with all the integrated handlebars that are coming now with bicycles, there's really not much to change, especially with the cables integrated. Even if you want to change the stack, so the number of spacers under the stem, it became harder and harder for us. So in this case, it's important either that the client that comes to visit you comes with the right bike, with the right size, with the right cockpit, or you basically make recommendations based on your experience that the rider would need, for example, a longer stem or a wider handlebar, narrower, and so on. So unfortunately, bike fitting nowadays became more and more focused on the clits and the saddle. But that doesn't mean the handlebar is not important. It's just on a daily basis, sometimes it's harder or more expensive for the client to change that. So, for example, saddle height is going to affect the lower limb joint angles. Then we'll have the functional reach and stack, again, trunk angle, arms joint angles, and center of gravity. And clit position will affect where the knee is going to travel in the lateral plane or in the frontal plane. One of the latest papers that's been submitted, and we've been taking part, it's a Delphi method led by Priego Quesada, a Spanish scientist, a great scientist, and it's been submitted. Basically, it's a consensus how bike fitters actually measure and determine the saddle height. So the paper is not published yet. It's been submitted. Actually, it's been submitted last year, so it's 2023. And it's under the review at the moment, but it's important to know how at the end of the bike fit or prior to the bike fit, how do we determine saddle position on the whole bike position? And basically this is more to gather your attention and to direct you. Once the paper is going to be published, I would encourage you that you use these methods, because it's important that all the bike fitters worldwide, that we work kind of on the same level of defining the bike geometry. Some of the things, and I can tell you firsthand because I am co-authoring this paper as well, and there was a lot of comments that we've submitted, maybe too many, and we didn't agree on everything. So some of us have been using certain arbitrary values and others been using other. None of us had a really justified opinion, but we just had to agree at the end on one. And I know that once the paper is going to be published and we'll agree on that, I'm happy to change the practice that I've been using for the last 10, 15 years in bike fitting business to basically be aligned with everyone else worldwide. So saddle height, I would say, is the first thing that comes to my mind when we speak about bike fitting. And saddle height has been shown many times in scientific literature that has a direct and a substantial, significant effect on performance, on comfort, and especially on the injury risk. Mainly knee joint is the one that's most affected. And in bike fitting, if we have to pinpoint one parameter that's going to dictate and say what's your saddle height, it's going to be set based on the maximal knee angle. So maximal knee angle is, we have to again be very careful here how we're reading the knee angle. What we have here, this is knee flexion. So when the leg is fully extended, speaking, is almost 180 degrees. It never is 180 because the length marks, the points on the bones are not always in a straight, well, almost never in a straight line. There's about 6 to 20 degree of flexion present even in standing still. But then there is a biomechanical knee angle measurement, and that's this one here, like an extension of the femur and then the angle of this. So why do we need to be important? Because the smaller the angle here is, the lower the angle, and vice versa here. So the smaller the angle, the more flexed the knee is. They're both measuring the same thing. So it doesn't really matter which one you are using. It's just important that you can interpret the data you want to use in your daily practice. What's also important is, and this comes from the paper I mentioned earlier, that we published in Journal of Sport Sciences, is according to the method that you're using, there are variation in the interpretation, which means, for example, what you're going to see here are 3 saddle heights, and these saddle heights were set according to the manual goniometer, like it was historically used in bike fitting business, defined by Andy Pruitt in the early, I think 2000, and this method set it up, and then we recorded what's the actual knee angle under dynamic conditions using 3 different motion capturing systems. The black graphs presents 3D kinematics, 2D kinematics, I'm sorry. Then the dashed line is 3D kinematics using Vicon, and then the white bars, you can just simply ignore it. It's something that most of you have never heard about. It's an electrogoniometer that's been used mainly in physiotherapy, but it doesn't really work in cycling business. So, but what I want to show you that there is about 2.5 degree difference in between the 3D and 2D kinematics. And in this case, the 2D kinematics that was used was a very high speed and technology, not some iPhone with a lot of the fisheye. So it was professional 2D cam with 300 hertz or 200 hertz. So if we go to the recommendations, I would say when using a 3D motion capturing system, based on the scientific literature, a bulk figure should be somewhere between 140 and 145. Now, having said that, that doesn't always apply to everyone because people are different in terms of their morphology and they have different needs and goals. But today, as I said, we are speaking about the fundamentals, and that's why I want to stick to some reference value to leave you with. And if you will invite a rider coming in and you're going to use a 3D kinematic software to analyze the knee angle correctly with all the places, you are not going to miss by a lot if you set them up somewhere between 140 and 145 of the maximal knee angle. Now, the maximal knee angle, here is another thing that you need to be careful is defined by whenever the knee is extended the most. But some of the scientific literature is using a different approach. It's using what's the knee angle at the bottom dead center. But in that case, most of the time is not the maximal knee angle. So it's important to understand this, that you use the right referencing system when you want to apply certain knowledge from the white papers into your daily practice. So a little bit about the fore and aft position before we start. Moving the saddle backward and forwards most of the time affects also the seat height. Because of the saddle, of the effective saddle tube is under the angle, if you're just gonna change the saddle far enough, you will see that the height, the saddle height, is not the same between 1, 2, and 3 positions. So what you have to take into account whenever you're interested, how moving the saddle backwards or forwards is gonna affect the biomechanics, you have to keep in mind to ensure that the saddle height remains the same. Otherwise, you may have a totally misleading result that's not going to be easy to explain, especially when you're, for example, interested in some other aspects of, for example, how the center of gravity movement is changing. It may change due to the lower or higher seat height when changing the angle. So it's important that you're ensuring that it's traveling in the same position. So when you're going to be moving the saddle forward, you have to raise the saddle, and vice versa. When you're moving the saddle backwards, to ensure the same saddle height, you have to lower the saddle. You can simply just measure that. There are some formulas that you could, Bolton and I use. Is, for example, if you change the saddle forward by 1 centimeter, you should change the saddle between 0.5 to 0.7 centimeters. But that mainly depends on the angle of the seat tube. Now, I'd say traditionally, again, or historically, saddle fore and aft formula or position was defined by the so-called knee over pedal spindle method. So they used the plumb line. They would set the cranks horizontally, that they would be pointing forward, and then they would drop the plumb line somewhere from the posterior part of the patella. That should not exceed going past the pedal spindle. Now, this has been shown in science that is just simply wrong. So I've intentionally put some scientific data here, quite recent data from Maynard, a French group from 2020, and they were actually recording tibiofemoral and patellofemoral forces, which you can see the plots here. And they've shown that moving the saddle forward, and this illustration here shows you that they were looking at the same saddle height. So they actually tested the fore and aft position and not the saddle height difference. So they tested it correctly, that there is a statistically significant difference in favor of the forward positioned saddle. That means ignoring the recommendations of the knee over pedal spindle can simply be ignored. Now, having said that, knee over pedal spindle is still an important parameter, but not from the fact that you stick to it as a limit. Say you cannot go past the pedal spindle. Just use it as a reference value when you're changing by how much have you changed the position of the knee over the pedal spindle. But don't make any conclusions based, okay, we can't go more forward because of X, Y reason. Like back in the day, they were saying that you're putting too much force onto the knee, which Maynard and the group showed contrary, that actually if you want to reduce the loading of the knee, put them forward more. So that's it's a very good study, and I only hope that more studies like that would follow in the future. Now, in the STT software, there is a knee over pedal spindle calculation in the results. Basically, at the beginning, when you before you start the measurement, you have to just measure how far the marker that you put on the lateral condyle is actually behind the patella. And once you do this, this parameter KOPS, which stands for knee over pedal spindle distance, here shows you where relation to the actual pedal angle you are. So a very useful parameter to record how much or by how much are you moving your saddle backwards and forwards, and maybe how that affects either comfort or other parameters that you're focusing on. So on to the, in my opinion, a very too many times ignored parameters, but for me, a very, very important parameters that I just love using when I'm doing some basic bike fittings, is called the center of gravity. So what center of gravity essentially is the point where the distribution of the weight of the body is equal in all directions. Imagine that if you could virtually grab this skeleton or yourself by this point, so the arrow is indicating that the center of pressure is somewhere here, you would be balanced in every single direction. So how this is calculated, it's basic biomechanics in a way. When you have a marker set like this one here, so this is STT software, and this is the marker set for bike fitting. And then you have a tablet which dates much back, and they've calculated that, well, they've actually measured on cadavers, measuring bones. Each bone, each segment, which is defined between point A to point B, so this is a segment, has a center of mass and has a certain mass. And when you put all those segments into the, let's say, less basic equation, you get the center of mass of the total body. So I think that STT is using something that's called free body model that Winters pioneered. They make some assumptions around the head, and it's very accurate in terms of showing where the center of gravity is. But the best thing is it's displayed in real time. So what you see here, if I would be able to zoom in here and I could spin that in three-dimensional space, I could see how the center of gravity is moving left and right, back and forward, or up and down. So a very useful parameter. But why do I find it so important, and in relation to the fore and aft position of the saddle, is simply because we found that whenever the center of gravity is positioned further away from the vertical line crossing the bottom bracket, a little bit more, or maybe in some cases too much pressure is put on the upper body and the arms and the hands. And in my experience with daily riders, commuters, and recreational riders, we see a lot of problems with hand numbness, and most of the time the hand numbness comes from too much weight on the front. Yes, there's also the angle of the arms, or the reach is being too long, and so on. This is all very important. But when we speak about the distribution of the weight, knowing where the center of gravity is helps you a lot. And vice versa, when we speak about the saddle problems and having, for example, too much pressure on the seat bones, one way is obviously to change the saddle and redistribute the pressure onto other contact points. But if the pressure mapping shows that the distribution of the pressure is correct and you just want to unload the saddle, in that case, you may be willing to move the center of gravity a bit forward to put more load onto the hands. So as we talked before, we have only five actually, contact points, and this is where we're playing. And two of those contact points and spinning continuously, these are the pedals, and only the saddle and the handlebars are holding you in the position. So when you change the whole center of gravity, so let's say you move the handlebars and the saddle backwards or forwards as a rigid object, in that case, you can manipulate where you're going to distribute more weight, either on the saddle or more on the hands. And as we know, most of the bike fits is tailored to the needs of the individual. There is no recipe where the center of gravity must be. But if I have to say the average non-injured, with no problem of comfort, road cyclist, center of gravity should be just behind the line dissecting the center, the bottom bracket. So it should be behind the bottom bracket. That means that around 60% of the body weight should be carried by the saddle, and about 40 with the handlebars. Not to everyone, but just as an average bulk figure. So the goal of the bike fit, when we speak about the saddle fore and aft position, if our aim is performance, power, TT or tri aerobar positions, and in some cases unloading the knees, put the center of gravity forward. If you want to minimize the hands and arms loading because you have numbness or maybe some pathologies coming from the office working too much with the computer mouse and you have a carpal syndrome or a thoracic exit syndrome, in those cases you want to put the center of gravity back. There's also a scientific literature indicating if you want to activate the glute max a bit more, that moving the whole center of gravity backwards would increase the activation of the glute max. How that directly transfers into performance, it's too early to tell, but it's definitely an impact. So nonetheless, I don't want to end up with a recipe, this is how you should do it. I want to end up with the fact that changing the saddle back and forth will affect where the center of gravity is going to be. And if you have the ability to measure the center of gravity, like in real time, very accurately with STT 3DMA software, you have a very vital and important information used in a process of bike fitting. Last but not least, we spoke about the clit adjustments. I just want to leave it here. Knee travel, or the direction of the knee travel during the flexion extension phenomenon during the cycling, is directly proportional to the clit orientation. A good analogy would be if you stand up right now and you face your toes outward, so you put your hips in external rotation, you do a squat, your knees will travel laterally outside. If you face your toes inside, that you do internal rotation of the hips, and you do a squat, your knees will go inwards. And that's exactly the same on the bike. So set the orientation and then monitor how the knees are traveling. This is again a screenshot from the software, a wonderful graph that you can see. This is the frontal plane, knee movement up and down and left and right. And in this case, I've played this just for the sake of this lecture, a poorly set clit and a very well set up clit. So basically, by manipulating the clits, unless you have force pedals like I do, where you can record torques of ground reaction torques, this is a great way to play with the knee and the clits as well. Another important thing that you can, from the kinematic perspective, and I believe too many times ignored, is the pedal angle or the foot angle. And there is quite good literature out there since 2010 and back, showing that dorsal flexion or plantar flexion during cycling exhibit different performance outputs. And generally, the conclusion of all the scientific literature says that whenever you have a rider riding more in plantar flexed position without doing any ankling, so let's say preventing the heel drop, the economy and the gross efficiency is much better than the in dorsiflexed position. So there is some statistically significant differences. And in a study that we performed, you controlling for the pedal angle, which is in direct proportion to the foot angle, it shows that index of effectiveness direct to the pedal forces is substantially, significantly increased during the plantar flexed position compared to the dorsal flexed position. Now, having said that, in STT software, you have ankle flexion and you have foot angle to horizontal. And that correlation of foot angle to horizontal to pedal angle is almost 100%. So great, you can use this and then it goes, basically you use this very important parameter to adjust the pedaling technique. Many times this is hard to do as a bike fit process, but in a process of bike fitting, you can manipulate by just verbally instructing the rider how to pedal, or you can hold the foot and teach them how to pedal to prevent that dorsiflexion. But then using the kinematics, you can calculate how effective this manipulation has been. Another important, trunk angle. There is a big misconception how the trunk angle was in past calculated. On the left-hand side, traditionally they just used the greater trochanter, so the segment of the femur, and then they just assumed that the whole spine is a rigid body. Now, again, Wendy Holiday and Jeroen Swart, they pioneered this, and they've re-established the equation how to correctly address the trunk angle is by using the lumbar segment as the segment in the calculation. So in STT software, even though the naming is not the most the best one, which I know they're working on to changing, but the calculation, the equation is already correct. So again, this will help you a lot, especially in this relation to the scientific literature, when you have the lumbar kinematics, the lumbar inclination, that you have this angle calculated correctly. And lumbar kinematics has been in a very close correlation between low back pain cyclist and cyclists with no low back pain. So on the graph on the right, you can actually see that the number of time spent in the lumbar flexion was much higher in low back pain patients compared to the non-low back pain patients. So before I finish and go to the take-home message, there's a very important feature in the software that I really like to use is the comparison. So a reference, when you get a client coming in with a problem and saying, right, I've got too much pressure on my hands, I've got too much problem with certain parameters, it doesn't really matter. You analyze them in their baseline. This is how I start my bike fitting. I start with the baseline. I want to see all the biomechanical parameters I can measure, and then see how all the manipulations that I'm going to do, handlebar change, cleat changes, saddle changes, everything will affect, and how that's going to change the movement. And when you have load reference value like you have it here, so that's the, let's say that's the finish, the end product, and this is how they started, you can compare so many things. And in this case, on the right place, I just want to show this is a small manipulation in the saddle position, and look at the change in the center of gravity, how much it went backwards, and it, for example, released in this case the pressure on the shoulders and the tension of the back, and just causing them to ride for longer and further. So a very, very good feature. It's good for you. It's good for the client. You can show them, say, look, this is how you came. This was your original position. With small manipulation in the saddle position, cleat position, handlebar position, this is the end product. And I believe because of this and this change, your riding is going to be more comfortable, it's going to be safer, and you're going to be faster. And bottom line is that's the goal of the bike fit, and this is why they pay you money. So I would strongly advise you, if you don't use softwares like that, get onto it, contact the guys and start using it. So a take-home message: use a reliable motion capturing system, be aware of the measurement error, and the foundation of the bike fit is this synergy between the contact points. We've talked about lower extremity angles, trunk angle, center of gravity, and these are the three fundamental variables to look at during the bike fit. And to finish it off, if it's good for them and if it's good for me, I'm pretty sure it's going to be pretty good for you as well. So thanks for sticking with me for the whole webinar, and I'm open for questions now.
Thank you, Borut. Super didactic and very interesting session. I would like to invite everyone to launch some questions now. The questions can be launched very, very easily. So there is a small icon in the bottom right from the screen, sorry. And if you press that button, you can type them down, and Borut and I will answer them one by one. At this moment, I think there are some questions that you can be answering, Borut, whenever you want.
Okay, so I'll start with Rahul. Does the fundamental be the same for mountain biking? I would say pretty much yes. I mean, mountain biking, it's the principle. And in terms of knee angle, pedal angle, this kinematics from the hip down should be the same, because you still have to push on the pedals and you have to take the bike forward. So in my opinion, yes, except the trunk angle and the upper body position. That's probably a bit different. Okay, I've answered this one. So the system has no anterior patella marker and does not create the KOP using the lower extremity markers. So Desmond, you asked about the knee over pedal spindle. Not sure if you've noticed when I spoke, there is the marker goes to the condyle, but you measure the distance, the horizontal distance to the patella, and you type this in. So when you speak about the parameter of the knee over pedal spindle, it's in direct relation to the patella. So that's being calculated automatically. So you don't need to do any corrections afterwards.
Exactly.
Okay, yeah, I think I just answered your question as well. Okay, Fadi asked the question, do you start your bike fitting session from the cleats, then saddle, then handlebar, or the other way around? This is a very good question. I start my bike fit with the conversation, obviously, and then I want to see the baseline. I don't change anything. Everything goes onto the bike as it is. Unless I see there's a big problem with cleat setup, then sometimes I just change that at the beginning. But normally the cleats go into sort of a baseline position at the natural stance to look at how their foot are being when standing still or sitting, how this way, swinging, and then set up the cleats accordingly. Then we start with the saddle and we follow with the handlebar. But sometimes we do the other way around. If the person goes on the bike and I see this Superman position when the handlebar is like 3, 4, 5 centimeters too far, then we do the basics at the beginning and return back. But if everything's okay in that case, yes, that's the protocol. Regarding KOPS measurement in order to avoid error of marker patella distance, could be okay to use 0 millimeters distance to set for KOPS. Yes, you could, but then you basically need to read the data by yourself and using that by yourself. But I think it's such a basic mathematics. It's one value minus other value that I would stick to it to what it is. The other thing is when you have 3D kinematics, it's the bike could be slightly under the angle or something can change, and in 3D kinematics, that's taken account into. And I would say if you're just going to type in and trust the algorithms that STT are using, you're doing a much better job. But you could, if you put 0 millimeters, you will actually see the distance of the marker to the pedal. So in that case, then it's up to your interpretation to use it correctly. Fatigue may alter the position of the rider. Yes. So Jose asked about the fatigue. That's been shown. 3 main things happen during fatigue. You posteriorly rotate your pelvis, you increase your shoulders going up, and you drop your heels. So you go in dorsiflexion. I try to avoid fatigue. So the intensity of the during the bike fit should be high enough to make them pedal not jumping on the bike, but at the same time, don't sweep them too much, because then you're basically not doing any manipulations. You're not reading kinematic data manipulations because of the changes you're doing, but because of the fatigue. But having said that, what I really like to do at the very end with the end position, I put them to the max just to see how the position will change, if it will change, when you put, let's say, above their FTP or even more. Only for 30 seconds, record the same kinematics and compare the same position to the lower power. And in some cases, it may happen that you see a big change, and then you ask your questions, why? What happened? What changed? And sometimes the answer is simply more muscles got activated and the movement changed in that case. But that's a little bit less fundamentals. Saddle position change rather is racing both road and track. Steve Nash asked the question about track. I'll be honest here. Track cycling in Slovenia is close to non-existent. And we have one track now, which I also use for aero testing, but aero guys, I mean, the track guys are really good at biomechanics. I love studying them, but I don't work a lot in terms of optimizing them. And why their biomechanics is so good? Because they always have to cover the same distance under the same conditions, and the only tool they use is a stopwatch. So they are how to say, experimenting what position would get them around the lab fastest. And I'm pretty sure for that it's one of the best ways to test it. And no kinematic system could be better than just simply measuring, saying, look, you're faster. That's it. Guillermo, any questions you want me to select? So I think there's a few more on knee over pedal spindle, but I think we've answered that. Okay, so Shafi asked about the ankle position should be like whether it's an internal external rotation, as like for aerodynamics are this used to make the knee more abducted. Are you sure about that? Because in my opinion, when you've done the aero tests, every time you change the knee going inwards or outwards, you're actually increasing your area. And that essentially means you're increasing your CDA. So aerodynamic riders, I would say, if you want to be the most aerodynamic, try to be in a straight line as possible. That's going to be your frontal area is going to be the smallest. So I think it's a misconception going inwards. Now, again, aerodynamics cannot be guessed. So I don't like saying this makes you more aerodynamic than that, but you have to measure it using a wind tunnel or track testing and only then making conclusions. But nonetheless, you cannot, for the sake of aerodynamic benefit, risk an injury or reduce too much the loading. And you have probably seen, for example, position of Pogacar on time trial or even on a road bike. People are making conclusions. I was looking some YouTubes that I'd be happy to comment on some other occasion of how his position is not aerodynamic, etc. You cannot make this conclusion from a YouTube. I'm sorry. You have to measure it, and we have measured it, and we've done a lot of tests of that. So don't make conclusions based on just simple movement. Measure the aerodynamics and then done the conclusions then. Jose has another good question. What do you think about changing the athlete's position, cleat and saddle position, based on a rider's terrain intensity of competition? Yes, we have done that. But again, these are not fundamentals. This is pro level. A rider riding Tour de France or multi-stage or racing a World Championship or Paris-Roubaix position, I would position them differently. So winning uphill or winning on flat, really short, fast races, there are other priorities to set. These changes are not dramatical. These are millimeters, but it allows them to stay from start to the finish in a comfortable position. And especially around if there's any saddle soreness and stuff, you cannot afford saddle soreness and try to win the Tour de France, because in the last week you won't be able to sit on the bike. So that needs to be set. Guillermo, you want to choose any? There's a technical question about if it's possible to connect a rider's heart rate and power in STT system.
Yeah, at the moment we are developing that the integration with power pedals and power cranks. We are starting integrating the power cranks from the brand Rotor, but once this integration is done, any power meter that can stream the power over ANT+ protocol will be ridden by 3DMA and will be shown in live during the normal activity. Yeah. So this is coming in the future versions. Yes. At this moment, it's not ready, but this is coming.
It's coming. That's good. Okay, maybe one last question for me. Vit asked the question, does saddle angle affect saddle height? It depends. So basically, when you change the saddle angle, it depends where the saddle is being clamped. So you have saddle rails. If it's clamped, I'm going to use my, well, I can actually use my saddle, which is here. If it's clamped here and you change the saddle angle, the sitting point, that's going to increase the saddle height. So you see that.